Good morning, everyone. Today we are going to see the second series of the online lecture videos. Today's topic is about solution of higher order ordinary differential equation. Actually, it is the extension of the previous video. Today we will see what are the key highlights of today's session. The higher order ODE, methods to solve higher order ODE, extension of the Wronskian that we have already discussed in second order case, concept of independence of solution, basis of solution, Euler-Cauchy's ODE of second order, Euler-Cauchy's ODE of higher order. So as an introduction, I will tell you two more sentences. That is, in this session we will solve ordinary differential equation with higher order derivatives. All the procedures are same as in the second order ODE, except that we have to find more higher order derivatives to find coefficients using method of undetermined coefficients. Then what is new in this approach? Here also we will solve ODE in 3 stages as in the case of second order ODE, but in stage 2 we have to find more higher order derivatives to equate coefficients. That is the difference. So take much care in finding particular solution. So next idea is linear independent solution. When we call a set of solutions y1, y2, etc. yn are linearly independent, the linear combination c1 y1 plus c2 y2 plus etc. plus cn yn equal to 0 is possible only for when c1 equal to c2 equal to etc. equal to cn equal to 0. That means in this linear combination expression all the coefficients of yi's are zeros, then they are linearly independent. If some of the coefficients c1, c2, etc. are non-zero, then the corresponding set of solutions becomes linearly dependent. The next topic is a basis of solution. The set of linearly independent solutions that spans the entire space of solution of an ordinary differential equation is termed as basis. So a basis should be linearly independent set and it will span the entire set of solutions. Then there is a natural question, how to check linear independence of solution. The easiest method is the Wronskian method. In that case we calculate the Wronskian. If the Wronskian determinant is not equal to 0, then the set of solutions are linearly independent. Here note that if y1, y2, etc. yn are solutions, we write first row with these solutions y1, y2, etc. yn. In this case I consider only 3 solutions y1, y2, y3. That is why that 3 solutions come in the first row. Then second row is actually the derivative of the elements in the first row. Similarly, third row is the derivative of the preceding row, that is derivative of y1 dash, y2 dash and y3 dash. If the system has n solutions, then automatically first row contains n solution, second row contains n derivatives, etc., etc., and finally nth row contains the derivative of the n minus row. So automatically it is an n by n determinant. Then concept of general solution. Suppose y1, y2, etc. yn are solutions of an nth order ODE, then the linear combination of these solutions is again a solution. That solution is called general solution. That is, mathematically y is equal to c1 y1 plus c2 y2 plus c3 y3 plus etc. plus cn yn. This is nothing but a linear combination of the set of given solutions, and this solution is considered as general solution. Then we consider an example of linearly independent set of solution. So question is, we have given 3 solutions, y1 equal to e raised to x, y2 is equal to e raised to 2x and y3 equal to e raised to 3x. We have to check whether these set of solutions are independent or not, linearly independent or not. We are going to use the Wronskian method. So first of all I write the formula for Wronskian. Wronskian is nothing but a 3 by 3 determinant in this case. First row contains the given solution, second row contains the solution of the derivative of the first row, third row contains the derivative of the preceding row. Like that, I substitute the values. First row, the solutions e raised to x, e raised to 2x and e raised to 3x. Second row is the derivative of first row, third row is the derivative of second row. Now we expand this determinant above the first row. So I take e raised to x into a sub-determinant obtained by deleting the column and a row containing that e raised to x, minus second element into the sub-determinant obtained by deleting the column and a row containing this e raised to 2x, this one, plus the third one e raised to 3x into the submatrix which does not contain the row and column containing e raised to 3x, that means this portion, small portion. Then I expand these 2 by 2 determinants and simplify this expression. I got 6 e raised to 6x minus 6 e raised to 6x plus 2 e raised to 6x. These are same terms. When we subtract 6 e raised to 6x from 6 e raised to 6x, we got 0. So the only answer is 2 e raised to 6x. That means here the Wronskian is not equal to 0. Whatever be the value of x, e raised to 6x never becomes 0, and therefore Wronskian equal to not, Wronskian not is a non-zero value. So these set of solutions, y1 equal to e raised to x, y2 equal to e raised to 2x and y3 is equal to e raised to 3x are linearly independent. Now we move on to a simple problem to solve a higher order ODE. Problem is, solve the initial value problem y triple dash plus 3y double dash plus 3y dash plus y equal to 30 e raised to minus x, which is satisfying the initial conditions y of 0 equal to 3, y dash of 0 equal to minus 3 and y double dash of 0 equal to minus 47. So remember, when we have given an ODE with some initial conditions, then it automatically become an initial value problem or IVP. In the case of initial value problem, we have to calculate arbitrary constants using this initial condition. That is only difference in the case of initial value problem. So as a first stage, we write down the auxiliary equation and calculate homogeneous solution. So the auxiliary equation corresponding to the left side is, from y triple dash I can write m cube, from y double dash I can write m square, that is 3 into m square plus, this plus is here, 3 into y dash, corresponding to y dash I take m raised to 1, that is m, plus y is actually 0th derivative of y, so m raised to 0, 1 into m raised to 0, sorry, is 1 equal to 0. This cubic equation can be factorized as m plus 1 whole cube. I simply write m plus 1 into m plus 1 into m plus 1 equal to 0. Then the roots are, the first m, that is m1, that is equal to minus 1, second m, that is m2, is again minus 1, third m, that is again minus 1. So m1 equal to m2 equal to m3 equal to minus 1. Look, all these roots are minus 1, it is a real number and but equal. So by rule, yh can be written as c1 into x raised to 0, that is c1 itself, plus c2 into x raised to 1 plus c3 into x square into e raised to minus x. That is our homogeneous solution. As a second stage, we are going to find particular solution. To find the particular solution, we think about the right hand side function r of x. Here r of x is an exponential function 30 into e raised to minus x. But see here, e raised to minus x is the functional part. This e raised to minus x repeat 3 times in the homogeneous solution. c1 into e raised to x first time, c2x into e raised to minus x second time, c3x square into e raised to minus x third time, and therefore we have to use some modification method. That modification method is like this: we multiply an e raised to minus x term by the power of x, which repeats how many times in the homogeneous solution. Here e raised to minus x repeat 3 times, so we multiply by x cube. So c4 is the arbitrary constant. So the Gus function yp is equal to c4 x cube e raised to minus x. The x cube is from here, e raised to minus x repeat 3 times, that is why x raised to that number of repetitions. Then we calculate yp dash, yp double dash and then yp triple dash. Because yp is a solution, it should satisfy the given ODE, So we have to calculate these all the derivatives. That is the only additional step. This yp triple dash is the additional step as we consider from the second order ODE. Now we substitute all these things into this ODE. Yp triple dash plus 3y double dash p plus 3y dash p plus yp is equal to 30 e raised to x. And all these terms yp triple dash etc. are taken from this previous step. From here, yp triple dash, yp double dash, and again yp. So it's a lengthy expression, that is why I skipped that step. Anyway, in every term there is a c4 and e raised to minus x. For convenience, I take e raised to minus x to the right and c4 to the left. The remaining terms contains polynomial in x, that is c4 into f of x and e raised to minus x equal to 30 e raised to minus x. The next step is the straightforward. The idea is we simply equating the coefficients of both sides. The right side coefficient is 30 for e raised to minus x. Left side the coefficient of e raised to minus x is c4 f of x. That is c4 into this big expression equal to right side coefficient 30. But remember, in this equation right side is a constant. So we have to compare the constant in the left side. The left side constant is nothing but 6 into c4. 6 into c4 is equal to 30. So c4 is equal to 30 by 6, that is 5. The only arbitrary constant is c4. We calculate c4 here. So we substitute c4 in the place of c4 in this equation, that is 5. Yp is equal to 5x cube e raised to minus x. So we move on to the last step, that is finding general solution. General solution is simply yg is equal to yh plus yp. It can be written as y itself. So y is equal to c1 plus c2x into c2x plus c3x square into e raised to minus x plus our yp. Yp is 5x cube e raised to minus x. Now to find the initial value problem completely, to solve an initial value problem completely, we have to find the c1, c2 and c3. For that I will use the coefficient, the initial values. Y of 0 equal to 3, y dash of 0 is equal to minus 3, y double dash of 0 equal to minus 47. For that I write y dash and y double dash. So I rewrite y here, calculate y dash, calculate y double dash. Then I put x equal to 0 on the right side and the corresponding y on the left side. So I got like this. Y of 0 is equal to 3 means I put x equal to 0 here in the right side. So all the terms except that c1 contain x. So all these become 0. The e raised to 0 is 1. That is why c1 into e raised to 0, that is c1. Left side value for y is actually y of 0 equal to 3. Y is equal to 3. We put that 3 here. So c1 is equal to 3. We apply the similar idea in y dash and y double dash with the values 0 for x and minus 3 for y dash, 0 for x and minus 47 for y double dash. So we finish c1 equal to 3, c2 equal to 0 and c3 is equal to minus 25. I simply substitute these c1, c2 and c3 in the original solution. I got y is equal to 3 minus 25x square into e raised to minus x plus 5x cube e raised to minus x. But it is very important to note that the only change happened in the homogeneous solution. The particular solution, there is no arbitrary constants. Only arbitrary constants c1, c2, c3 are present in the homogeneous solution. Okay. Next is the extension of variation of parameter to higher order ODE. As we already know, variation of parameter is a straightforward technique to calculate yp without any comparison of coefficients. So this method is actually an extension, that is to find the particular solution of a higher order ordinary differential equation. The general formula for nth order ODE is like this. It's very easy to remember. Yp is equal to, we start from y1 itself and move on y2, y3 etc. up to yn. Then there is an integrand. The integrands are like this: w1 by w into r of x dx. See, this w1 by w is our Wronskian. If there is y1 is outside the integral, w1 is in the numerator. Here y2 is in the outside, so the integral contains the fraction with the w2 in the numerator. See, here is yn, so the fraction contain w1 in the numerator. It's very simple and easy to remember. Suppose if the ODE is of third order, there is only 3 solutions, y1, y2, y3. So the last term should be y3 into integral w3 by w r of x dx. That's all. Then there is one more thing you have to identify, that is what is w1 and w2 etc. w1. So w1 is actually obtained from w by some change in first column. w2 is actually obtained from w by some change in second column. Like that, w1 is a new determinant obtained from w by some change in nth column. I will explain what is the change with a problem. As an example, solve the ordinary differential equation y triple dash minus 6y dash double dash plus 11y dash minus 6y equal to e raised to 2x plus 1 by e raised to x using the method of Wronskian. So the left side is an ordinary differential equation up to third order degree terms, and therefore it is a higher order ODE. I write down the auxiliary equation corresponding to the left side, m cube minus 6m square plus 11m minus 6 equal to 0. So we can factorize it using a calculator, m minus 1 into m minus 2 into m minus 3 equal to 0. See, the product of these constants, minus 3 into minus 2 into minus 1, that is minus 6. Sum of these constants again coefficient of m square. Then pairwise product, take the sum of pairwise product, that gives plus 11. So roots are m1 equal to 1, m2 equal to 2, m3 equal to 3. These are distinct values and real numbers. So by rule we can write yh is equal to c1 e raised to x plus c2 e raised to 2x plus c3 e raised to 3x. Now we write the term associated with c1 as y1, the term associated with it c2 as y2, the term associated with c3 as y3. The next step is Wronskian. The formula to find Wronskian is w is equal to first row solutions, second row derivative of the first row, third row derivative of the second row. I fill y1, y2, y3 using our solutions e raised to x, e raised to x and e raised to 3x. Second row is derivative of first row, third row is derivative of second row. That's all. Now we expand the determinant about the first row. So e raised to x into the subdeterminant which does not contain the column of e raised to x and row of e raised to x. So this is a submatrix, and we expand this. So we get 6 e raised to 6x minus 6 e raised to 6x plus 2 e raised to 6x. These terms get cancelled. We got 0. So corresponding value is 2 e raised to 6s. We have already seen this Wronskian. Now we are going to find out w1. w1 is actually obtained from w. The change is in only first column. We first replace the first column by 0, 0, 1. Thus, that column contain 1 in the last position, 0, 0, 1. Then we fill y2, y3, y2 double dash, y3 double dash, y2 double dash, y3 double dash, etc. Now here the first column has a particular property. The first two elements are 0, last row is 1. So in order to evaluate determinant about the first column is easy. So we take determinant about the first column. So the only non-zero element is 1. So 1 into its cofactor value. Cofactor value is actually minus 1 raised to position sum. Minus 1 raised to, this is in third row, first column. Minus 1 raised to 3 plus 1. Minus 1 raised to 4. That is plus 1 into, we avoid this column and this row containing 1. Submatrix. We expand this. So we got e raised to 5x. Now you can guess what is w2. W is a new determinant obtained from w by changing second column. The same change, second column is replaced by a column containing zeros and last element is 1. Now we fill y1, y3, y1 dash, y3 dash, y1 double dash, y3 double dash as in the previous case. Then expand the determinant about the second column. So these elements contain non-zero value and all other elements are 0. So its position value is minus 1 raised to, this is third row, second column. Minus 1 raised to sum of that positional values. Minus 1 raised to 5. So minus 1 into, I elude this column and row. Then submatrix is e raised to x, e raised to 3x, e raised to x, 3 e raised to 3x. I expand it I got minus 2 e raised to 4x. Similarly, I evaluate W3. In this time, we replace the last column, the third column, by 0, 0, 1. Fill the values, expand the determinant about the last row. In this case, the position value is minus 1 raised to third row, third column, minus 1 raised to 6. So plus 1 into, we avoid this column and the row containing 1. So this submatrix. So its determinant is e raised to 3x. So we calculate W1, W2 and W3 from W. Now last step, that is calculating Wronskian. We simply rewrite y1, y2, y3, w, w1, w2 and w3 here, because we can easily substitute here without any mistake. I write the formula for the particular solution, that is yp equal to y1 into integral w1 by w r of x dx plus etc. I fill the values. Then e raised to 5x by 2 e raised to 6x. This 2 can be put here 1 by 2. This becomes 1 by e raised to x, that is e raised to minus x. Then multiply this e raised to minus x into the arguments. Then simplify this, then integrate. I do the same thing for all the three terms. And I simplify e raised to integral of e raised to x is e raised to x itself. Integral of e raised to minus 2x is e raised to minus 2x by minus 2, like that. Then club the terms of e raised to 2x and e raised to minus x. Here e raised to 2x contains two terms, so this minus x is negative. Here e raised to 2x by 2. Here again minus e raised to 2x by 2. I simplify this expression. I think this may cancel. So the complete solution is yg is equal to yh plus yp, that is c1 e raised to x plus c2 e raised to 2x plus c3 e raised to 3x plus minus x into e raised to x. This one is a mistake. Minus x into e raised to 2x plus 13 by 25 e raised to minus x. I will correct this mistake. Here this e raised to 2x by 2 is positive. Here e raised to 2x by 2 is negative. This get cancelled, only this term. Solution is changed. Here also we make this change. So the complete solution is like this. This is all about the higher order ODE and its solution, even using Wronskian. So today's session is over. We will meet next session with the remaining portion, that is a special case of higher order ODE, that is called the Cauchy's-Euler ODE of second order and higher order. Thank you.